In 1961, a meteorologist named Edward Lorenz was running a weather simulation on his computer. He wanted to re-examine a particular sequence, so he typed in a number from a previous printout. He typed 0.506. The computer's memory held 0.506127. The difference was smaller than a breath of wind, smaller than a raindrop falling 1 millimeter to the left. But within simulated days, his weather had completely diverged. Sunshine became storms, calm became hurricanes. The two forecasts shared nothing in common. Lorenz stared at the printout and realized something terrifying. The future isn't just hard to predict. For certain systems, prediction is fundamentally impossible. No matter how powerful your computer, no matter how precise your measurements. This wasn't a flaw in his model. It was a feature of reality. He had stumbled onto one of the deepest truths about our universe. Deterministic systems, systems with no randomness whatsoever, can behave in ways that are completely unpredictable. This is chaos theory, and it changes everything we thought we knew about cause and effect. For 300 years, science believed the universe was a clock. Newton showed us that every force has a law, every orbit has an equation. Given the positions and velocities of every particle, you could, in principle, calculate the entire future. The French mathematician Pierre-Simon Laplace took this idea to its logical extreme. He imagined a being, sometimes called Laplace's demon, who knows the position and momentum of every atom in the universe. For this being, Laplace wrote, nothing would be uncertain, and the future, as the past, would be present to its eyes. This was the dream of determinism. The universe is a perfectly predictable machine, and it worked beautifully. We predicted eclipses centuries in advance. We sent rockets to the moon using nothing but Newton's equations. We calculated the return of Halley's comet to the day. The clockwork universe seemed unstoppable. But there was always one nagging problem. Newton himself knew about it, a problem so subtle, so tangled, that he said it made his head ache. Three bodies, the sun, the earth, the moon, three objects pulling on each other with gravity. Simple forces, simple laws, but their combined motion, unsolvable. In 1887, King Oscar II of Sweden offered a prize, solve the three-body problem. Predict how three gravitating objects will move for all time. Henri Poincaré, the greatest mathematician of his era, took on the challenge. He didn't solve it, but what he found was more profound than any solution. Poincaré proved that no general formula exists. Three bodies interacting through gravity can produce motion so tangled, so interwoven, that the trajectories form what he called a homoclinic tangle, a web of paths crossing and recrossing with infinite complexity. He saw that tiny changes in starting position led to wildly different futures. Orbits that looked stable for centuries could suddenly fling a planet into deep space. He called this behavior sensitive dependence on initial conditions. Poincaré had discovered chaos 50 years before anyone gave it a name. But his discovery was buried. The mathematics was too complex, the implications too unsettling. Physics moved on to quantum mechanics and relativity. The clockwork dream survived. It took another 60 years and a computer to bring chaos back from the dead. Because the thing about sensitive dependence is, you can't see it with pen and paper. You need to iterate thousands of times, millions of times. You need a machine that never gets tired of repeating a simple calculation. Edward Lorenz was that man with that machine. His 1963 paper, Deterministic Non-Periodic Flow, described a set of 3 simple equations, a stripped-down model of atmospheric convection, warm air rising, cool air falling, nothing exotic. But when you plot the solutions in 3 dimensions, x, y, and z, something astonishing appears. The trajectory never repeats. It loops around 2 focal points in a shape that looks like a butterfly's wings. 2 trajectories starting almost identically, differing by 1 part in a million, will dance together for a while, then suddenly diverge. One loops left while the other loops right. They never reunite. This is the Lorenz attractor, the geometric face of chaos. In 1972, Lorenz gave a talk with a provocative title, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" He wasn't being poetic. He was stating a mathematical fact. In a chaotic system, disturbances below any threshold of measurement can amplify into macroscopic consequences there is no small enough to ignore. This is why weather forecasts break down after about 10 days. Not because our models are bad, they're excellent. Not because our measurements are sloppy, they're incredibly precise. But because the atmosphere is chaotic. Information about its initial state is lost exponentially fast. Prediction has a horizon, and chaos determines where that horizon is. But you don't need weather systems to find chaos. You don't even need 3 dimensions. Consider the simplest possible feedback loop. Take a number, multiply it by a growth rate, then multiply by 1 minus itself, a term that prevents unlimited growth. Feed the result back in, repeat. This is the logistic map. X next equals R times X times 1 minus X. 1 equation, 1 variable, 1 parameter. When R is small, say 2.5, the system settles to a single, stable value. Predictable, boring. Increase R to 3.2 and the system oscillates between 2 values. A heartbeat, still predictable. Push to 3.5, 4 values, then 8, then 16. The oscillations double and double again, faster and faster. This is period doubling, a cascade where simplicity fractures into complexity with increasing speed, and then at R equals approximately 3.57, the cascade reaches infinity. The system never repeats. It bounces wildly, apparently at random, across its entire range. Chaos from a single deterministic equation. But here's what stunned the mathematical world. Zoom into the chaotic region and you find windows of order. Stable cycles of period 3, period 5, period 7. Islands of predictability floating in a sea of chaos. Zoom into those islands and each one has its own cascade into chaos. The same pattern at every scale. This isn't just mathematics. Population biologists saw this exact pattern in fish populations. Ecologists saw it in insect outbreaks. Physicists saw it in dripping faucets. 1 equation, infinite complexity, written into the fabric of nature. In 1975, a young physicist named Feigenbaum was studying period doubling on his pocket calculator. He measured the ratio between successive bifurcation points, how much closer together each doubling gets. The ratio converged to a very specific number, 4.669. Feigenbaum tried a different equation, same ratio, a completely different type of mathematical function, same ratio. He checked dozens of systems, sinusoidal maps, Gaussian maps, cubic maps, all different equations, all with the same number appearing at the onset of chaos, 4.669201609. This is the first Feigenbaum constant. It's universal. Any system that approaches chaos through period doubling, regardless of its specific equation, will bifurcate at exactly this rate. Think about what that means. The route from order to chaos isn't unique to any particular system. It's a universal pathway. Like pi showing up in circles, Feigenbaum's constant shows up in the doorway between predictability and chaos. Water dripping from a faucet, electrical oscillations in a circuit, laser intensity fluctuations, heart arrhythmias. All of them approach chaos at the same rate. All of them are governed by the same deep mathematical structure. Chaos isn't random. It has its own laws, its own constants, its own geometry. If chaos isn't random, what is it? Where does a chaotic system actually go? The answer lives in phase space, an abstract space where each point represents the complete state of a system. Position, velocity, temperature, every variable gets its own dimension. A pendulum traces a circle in phase space. A decaying vibration spirals inward to a point. These are simple attractors, shapes that the system is pulled toward. But a chaotic system is pulled towards something far more exotic, a strange attractor. The Lorenz attractor is one example. It has a fractal dimension. Not quite two-dimensional, not quite three. It's approximately 2.06 dimensional. An object that exists between dimensions. On a strange attractor, nearby trajectories diverge. That's the chaos. But they all stay confined to the same geometric structure. That's the order. The system never leaves the attractor, but it never repeats the same path twice. This is the deepest insight of chaos theory. Unpredictability and structure coexist. A system can be simultaneously impossible to predict and bound by deep geometric constraints. The weather is chaotic. We can't predict whether it will rain in 3 weeks, but the climate has structure. The Earth won't suddenly become Venus. The strange attractor of Earth's climate keeps the system within bounds, even as the specific path remains forever unpredictable. Strange attractors are fractals, and fractals are everywhere chaos has been. Benoit Mandelbrot asked a simple question in 1967, how long is the coast of Britain? The answer, it depends on your ruler. Measure with a 100-kilometer ruler, you get one number. A 10-kilometer ruler gives a longer coastline, a 1-kilometer ruler, longer still. The coastline has no definite length, it's a fractal, infinitely detailed at every scale. The Mandelbrot set, born from another impossibly simple equation, z next equals z squared, plus c contains infinite complexity. Zoom in, and you find copies of itself at every magnification, an infinite depth from a finite rule. This is the visual signature of chaos. Simple rules, iterated endlessly, creating structures of infinite complexity. A fern leaf, a lightning bolt, a river delta, your circulatory system, the distribution of galaxies. Nature doesn't design with straight lines and smooth curves. It designs with iteration and feedback, with chaos. And here's the beautiful truth that Edward Lorenz discovered on that winter day in 1961. The universe is deterministic. Every cause has an effect. Every effect has a cause. The laws of physics never waver. But determinism does not mean predictability. The clock still ticks. We just can't read the hands.